everyone. My name is Aria Bonczek. I'm a spec ops software engineer here at Unity. And today I'm going to talk to you a little bit about the user-facing interface for ECS and the rest of the data-oriented tech stack. More specifically, I'm going to go into kind of the principles that we use to design the API and improve the APIs as time goes on, and how we can expect those principles to inform the way that we improve the API going forward. So before I start, let's get to know each other a little bit. So before I came to Unity, I worked at a studio called Darkwind Media, where, Darkwind represent, where most of my work focused on porting Unity games to consoles, a specific Unity game. And then after that, I was an engine programmer at Santa Monica Studio on the latest God of War title. And now I'm here at Unity, working on performance by default. And so the reason that I wanted to talk about this topic in particular is because I've been in both of those trenches. You know, I've shipped a Unity game, and I've enjoyed all of the simplicity and immediacy that Unity provides to its developers. But I also care very deeply about performance, and I care very deeply about engineering and solving low-level problems. So I wanted to talk specifically about how we can kind of bring those two topics together, make it simple and easy to solve those problems. So you've probably heard this phrase once or twice by this point, I hope. And I wouldn't bring it up again if it wasn't actually important. I mean, this is kind of the core mission of everything that we're trying to do here at Unity. And if you've been sitting in this room today, or if you saw the Megacity demo, then you're probably pretty familiar with what we mean by performance. But you might not be as familiar, or might not be as clear exactly what we mean when we say by default. Which really, as the Unity developer, like, this is the thing that's probably most important to you. The APIs and the tools that you use to develop your games are the direct interface. It's the first thing. If you can't even build something out of the APIs that exist, then you don't have to worry about performance because you haven't built anything. There's no game. So I wanted to talk a little bit about that today. So in this talk, I want to clear up a little bit about what we mean. There we go. By default, and kind of answer that question. I'm also going to walk through some specific examples about kind of how the API has changed over time and how we are currently even still working day to day on improving the API and doing a little bit better at providing by default. I also want to detail a few of the principles that go into how we think about and design those APIs. And using those principles, I hope that I can provide some context for how you can expect the API to change in the future. I mean, we're still in preview at this point, and as we kind of move towards that point of being production ready, we want to make sure that you're not slapped in the face all of a sudden when an API change comes in and everything's kind of insane. So the natural segue to talking about this is to talk about airplanes. And I promise I'm going somewhere with this. So I was scrolling through Twitter last week, and a friend of mine brought my attention to this article, which was written in 2016. It was written in The Guardian, called Crash: How Computers Are Setting Us Up for Disaster, which sounds like a very dramatic title, and I mean, it is for good reason. I mean, the article was basically about a particular type of aircraft called the Airbus 330, which was designed to be the safest, most advanced aircraft in the world and easiest to fly. I mean, the whole idea was that a pilot would be able to just take some controller, basically, and kind of move the controller in the direction that they want the plane to go, and the plane would just figure out everything it would need to move all of the rudders and move all of the elevators and actually translate that input into hardware instructions, essentially. But got a little ahead of myself there. And this works fine, and actually it worked pretty well until it didn't. Until a system like this requires a significant amount of information to actually be able to reason about where to move the plane. And if for whatever reason any of the systems that gather that information, any of the sensors or anything goes offline, then the plane immediately defaults back to manual mode because it doesn't want to use a system that could potentially put people at risk. But if a pilot spends 5, 10 years flying these planes on autopilot, they may not have all of the practice, and they may not have the actual understanding on how to fly the plane on full manual. And that's caused a couple of plane crashes over the past couple of decades, which, sorry for getting a little dark in my ECS talk, but I think it's important to talk about how failures in some other areas of technology can inform the way that we make games. So what actually happened here? There was a team of engineers, and they wanted to build some sufficiently advanced piece of technology that was just so easy to use that you didn't actually have to understand the problem that it was trying to solve. And that turned out to be a problem. By over-relying on the abstraction on top of the manual controls, when the challenge arose, when the pilot actually had to fly the plane on full manual, they didn't know enough about the system in order to do that successfully. And in the case of an aircraft, the consequences for that are much more dire than we have in game development. But at the same time, if something goes wrong during game development, and anybody who's shipped a game knows that challenges arise, it happens pretty frequently. If such a challenge arises, you need to be able to react to that. You need to be able to find that manual control. You need to be able to understand what's going on beneath the systems that you're working with, or else you won't be able to sufficiently fix your games. And if that stuff takes too long, then you start to crunch for hundreds of hours, and it's no fun. So what I'm trying to say here is that by default doesn't mean an autopilot. We're not building a system that is just going to kind of take your data and take your code and just fly with it. But don't get me wrong. Like here at Unity, we care very deeply about making it as easy as possible to develop your games and solve the problems that you actually want to solve, but not at the expense of understanding the systems involved in getting you there. We fundamentally believe we can make writing fast code as simple as mono behavior update is. And to do this, we want to provide what I'm calling utility over abstraction. An abstraction is something that hides what's going underneath. It hides the actual work being done so that you don't have to worry about it, and you can just keep using that abstraction any way you want. It's a black box. But with a utility, you can be empowered to be the experts of your own data by using a library, by using an API that allows you to transform and access that data in optimal ways, then in the most direct and transparent way as possible. With those tools, it becomes a lot easier to develop your games, and nowhere along that stack is any of that information lost. So I could keep talking about this and just say words for a while, but I think it'd be probably a lot more useful if we look at an actual code example of how this works in practice. So to do this, we're going to look at this move along circle system, which is code that you can actually find right now if you go to the GitHub entity component system samples that we have. This is real code that exists, and we're going to take a look at this code, and we're going to try to identify some of the places that we might be able to improve it and migrate it from using the old API to the new utilities that we have started developing and providing. So let's first take a look at how we're actually accessing the component data, which fundamentally is probably the most important thing about ECS. So here we've created this move along circle group structure, which contains all of these component data arrays, which are each kind of specified with different component types. And these are each of the component types that we actually want to access in our job. And then we create an instance of the struct and tag it with this little attribute, inject. Later on, in our on update function, we just take that instance and we access the contents of that structure, and we find, hey, cool, it's already filled with everything that we needed. We didn't have to worry about getting it from somewhere. It all happened kind of automatically, which sounds great, right? But what does the inject attribute actually do? To find out, we'll have to actually look through the code. So if we start by looking at the attribute itself, that's not very helpful. But it gives us a starting point. We can start here. We can look for other places in the code where this exists. And eventually, we come across to this big function here, which if you do a little digging and you look around, this is essentially happening anytime that we create a component system in ECS. And there's some stuff here that is like, OK, we've got some C# lists. That's probably maybe not the best thing that we want to doing a bunch of garbage collection just for tagging a single instance with a little attribute. But OK, fine. When you dig deeper, you get into something like this, which is probably a little small and hard to see, but it's just because of it's just this gargantuan piece of code performing all sorts of expensive things, C# reflection, and doing string comparisons. And this is happening automatically. It's happening regardless of whether or not you're explicitly calling it or not. By putting that inject keyword on, it's doing stuff behind your back. So let's take a look at some of the problems, right, that we've identified here. There's implicit behavior, which is pretty undesirable. This update occurs that code there isn't necessarily the update, but then update occurs every single frame of those injected component groups, whether you actually need the data or not. It just happens. And it also has a bit of an opaque life cycle. Like, OK, well, when does that thing get filled? I don't know. You'd have to look through the code and figure it out. And if there's something that invalidates the life cycle, that invalidates the data inside of one of those structures, then now you have to know that, right? You have to know to actually update those structures in your code. What can even be injected in one of those things? If it's not in the documentation, then we have to look in this big else if chain and try to figure out what we actually can use here. C# reflection, not our favorite. C# list, also not our favorite. String comparisons, so on and so forth. There's a lot of fundamental problems with this code. So not only is it opaque, not only is it difficult to tell what's actually going on, but it's also not actually performant. There are a lot of clowns in this car, and we want the clowns out of the car. So let's talk about what problem Inject is actually trying to solve. Really, at the end of the day, all we want to do is access our component data. We want to read it, do something with it, write it back. And we also, the nice thing that we have here is that we can actually filter the entities that we're getting by sets of component data. So in this particular example, we're only getting the position, move along circle, and move speed component data for entities that actually have all three of those things. So is there a better way that we could do this? Well, it turns out that if you follow all of that code, Inject is just a pretty slow way of making something called a component group, which is just essentially it's an explicit group of archetypes based on some kind of a query, some set of component types that you want to match for all of those archetypes. And the inject keyword just kind of tries to create one of these things every single frame. So instead of having the inject keyword handle this, why don't we just do it ourselves? Turns out that the code is pretty easy, and there's no clowns in that car. So pretty good deal, I think, there. So we've gotten a couple clowns out of the car, but we're removing the layer of abstraction that Inject provides around the data. But we're not done yet. Let's take a deeper look at another ECS concept here called the component data array, which on the surface sounds like a pretty sweet deal. I have some component data, I want to access it, and the system has given me a nice and friendly indexable array. Great. An array is just a pointer. So really all this is doing is just doing a pointer index offset to grab some data, right? Yeah, but come on, oops. That's not all it's doing. It's a little asterisk there in our little deal here. So let's take a look at what's actually happening. This is just the indexer. This is the get part of the indexer for the component data array. And it's doing this, there's a branch on a couple of different conditions. This move to entity index, it's updating some kind of a cache. What does it all mean? Well, apparently this is what it means. Okay, we've got some more branches, we've got some more loops, and this code is happening every single time. I mean, if certain branches fail, of course it takes early outs, but this code happens every single time that you try to access any piece of data using an indexer with a component data array. Oh, that's not what I wanted. So to talk about why this was actually necessary for component data array, just a quick review of how ECS chunks actually lay out their component data. An individual chunk is just a 16 kilobyte buffer of memory. And we fill per archetype, we decide how we're going to allocate out all of the component data into parallel streams inside of those chunks. And then each archetype keeps track of all of the chunks that are associated with that archetype. But all of those chunks aren't necessarily linear in memory. They kind of, there's one linear 16 kilobyte buffer here, one 16 kilobyte buffer over there. So in order to actually index into this list, this array of chunks, and actually grab the right data from the right entity, we have to do all of this bookkeeping to figure out, okay, well, which chunk are we in? How many entities into all of our chunks is this chunk? And that gets pretty slow. So let's do a little bit more clown counting. We have an abstraction that hides an implementation detail, which the component data array, for calling this thing an array, it's not actually an array. So we've, the abstraction has lied to you, and that doesn't feel very good. But even worse is that it has deceptive performance consequences. Whenever you access pieces of data from this thing, which accessing data from an array should be one of the fastest things that you can do, it turns out to be more expensive than that, especially when you're iterating out of order, because the system then has to recalculate, oh crap, you went backwards, okay, so now just making sure that I'm on the right chunk here, and I have to recalculate where I'm at, which is just no fun. And even if you're absolutely sure you're never accessing things out of order, and you're like, yep, I'm always doing it in the most optimal way possible, there's still other cases in the system where things can be accessed out of order. When you're accessing that data with an iJob parallel 4, for example, and one thread has finished its work and decides, hey, I need a little bit more work from another thread. I'm just going to steal this job over here and continue executing here, which is normally a great thing and kind of keeps thread occupancy really high. But now we are deliberately jumping around in that chunk structure on different threads just by stealing another job, something that's supposed to be a good thing, supposed to be an optimization. Lots of clowns in the component data array car. So let's ask ourselves again, what problem is this actually trying to solve? Well, at the end of the day, all we really want to do is read, transform, and write back our data. But another nice thing about having this data in an array format is that it's kind of nice. We can uniquely identify each entity that might be, and that unique identification might be necessary for certain problems. If you have, say, a hash map and you're adding information into that hash map based on some index, and you want to make sure that you can map the index of the entity to the index inside of that hash map later on and grab that data, you want to be able to have something like that. So given this, is there a better way to solve this problem? Well, we can do something called chunk iteration, which basically just means, why rely on this other structure, why rely on the component data array to actually get the data from the chunks for us? Why not go to the chunks and actually ask for the data ourselves? We avoid the cost of jumping between chunks because essentially you're going from chunk to chunk and just asking, hey, give me your pointer to your array, and I'm just going to index it, and you can just index that with no strings attached. I mean, you can't index it out of bounds, of course, but that's just kind of naturally how arrays work. And it's nice, and it also provides the ability for some really nice full per chunk optimizations. You can if there's some piece of logic that maybe you're going through a whole, each chunk by chunk and blasting through all this data, and maybe you have some way to predict, okay, well, for this chunk, I might not actually need to go through all of that data, and you can just completely early out of that chunk from the beginning. By doing things, if you understand your data, by doing things on a per chunk basis, it affords a lot of different optimizations that you can perform. So just to be sure, now that we've kind of looked around, okay, clowns are gone. No clowns in the component data array car, or in the chunk iteration car. But wait a sec, this chunk iteration seems kind of scary. There's a lot of extra code necessary just to access my data. Like, that's all I want. All I want is to just be able to read something, do something to it, and then write it back. And the cognitive load required to think, okay, well, I have these archetypes, and the chunks are laid out like this, and like it's too much to deal with if the code that you're actually working on doesn't need to know that. If you're not actually taking advantage of the way that things are laid out, if you just want to blast through all of your data, it's a lot of boilerplate and it's a lot of complexity that you might not necessarily want. Is there a better way? Well, I wouldn't be doing this talk if there wasn't. We have this concept called the iJob process component data, which is a nice new job type in the ECS API that allows you to explicitly specify which component types you care about. So like we talked about before with Inject and the component group, we've specified I want entities that have the position, move along circle, and move speed component types. And under the hood, the way that this actually processes your data is essentially identical to chunk iteration. So it avoids all of the nastiness of component data array, but provides the simplicity and provides the shorthand so that you can just say, I have some data, and I want to process it. And it's that easy. But there are some limitations with this. It's limited to just one component group at a time, right? You have this query of these three things, and it's going to give you a component group for those three things, and that's about it. So if you actually need to do some more complicated or more manual work, then you'll have to go to the manual APIs, like chunk iteration, in order to do that. So this brings up the idea of something called scaffolds, which is kind of the pinnacle, kind of the cornerstone by which that we're designing the ECS API. Scaffolds are high-level utilities, like iJob process component data, that encapsulate the low-level functionality. This decreases the difficulty of actually writing your code, and you can get up and running faster with ECS. But all of the ladders are clearly visible. As you start to use the system, you start to see, oh, okay, well, this is just, all this is doing is making a component group based on these things. Cool, now I understand how component groups work. Oh, okay, I looked into the iJob process component data code, and it's just finding all of the chunks. It's taking each chunk inside of that list and just going through them one by one. Great. So the ladders to the lower level functionality are clearly visible, and it helps you learn about and reason about the actual transformations going on. If you need a lower level version for some reason, it's not a huge leap to get there. You've already been familiarized with those concepts, and it's all pretty easy. And here's just a nice visual look at what this looks like. We understand entities. That's kind of the core concept of ECS. And we have this iJob process component data, but inside of there, we're doing component groups, and we're doing chunk iteration. And at any given time, you can just take those things outside of iJob process component data and use them directly. And you don't have to do this across your whole code base. You can just use this in the places where you actually need those lower level functionalities. So to kind of, I guess, sum up the different principles that I hope I was able to get across, is that we do care a lot about simplicity. We want it to be just as easy to write your code in ECS as it is in monobehaviors. And we also want to make sure that the cognitive load is as low as it needs to be. You shouldn't have to be worrying about a significant amount of complexity if your system and the actual transformations you're doing doesn't require it. But we also care a lot about transparency, utility over abstraction. We want it to be easy for you to move from one scaffold to another, which leads to incrementality. Being able to see, okay, I'm using this higher level API, but there's lower level stuff underneath that, and I know how that works. And lastly, we want these scaffolds to have a lot of lifetime value. Like I mentioned before, you don't need to move to the lower level APIs for everything. You only have to move to the lower APIs for the things that actually need those APIs, for the optimizations and for the code solutions to your problems that actually require that API. And there's plenty of work left. When I say we want ECS to be as simple as mono behavior, we're working on that. ECS is still in preview, and there's still a lot of work to do. iJob process component data still has a lot of boilerplate. Every single time you have to set up this job structure and write all of this additional code. Maybe there's another solution to that. We've been thinking lambdas lately, C# lambdas. And we'll see what that looks like once we've implemented that. Chunk iteration API could be a little cleaner, right? It's just, it's a little messy right now. Passing around these chunk component types is kind of awkward, and there's probably a better way to actually conceptualize that. And we want to provide other utilities, like just copying. If I just want a big native array buffer, I just want a real array of my buffer, similar to component data array, but actually fast to access, actually the thing that I want. We'd like to provide some utilities like that and other utilities as well. And there are, I'm sure, tons of concerns or some concerns that we haven't thought of yet. And for that, that's why we're in preview. That's why we're developing this out in the open. That's why we're talking about it, so that we can get some feedback from you guys about what your concerns are, what your problems are that you think that ECS doesn't solve, and either we help you find a solution with ECS as we have it, or maybe there's a little bit more work left to do. So I hope that I answered some questions about the ECS API and kind of how we've designed that. But if anybody has any other questions, now's a pretty good time. There are mics. There are microphones set up in the back, so feel free to go and ask a question.
How would you go about a rewrite of an existing game project with the new ECS enhancements, given that they're still evolving? So let's say I have a game that has about 20,000 lines of code, and with these new improvements, I would like to take advantage of the enhanced performance and the burst compiler. One question is, at what point of time are they going to be polished enough for me to go through that effort? And roughly, how would you go about a rewrite effort of an existing game?
Yeah, totally. I mean, to answer the second question first, just modularly, right? One piece at a time. I mean, that's the nice thing about ECS, and even as it pertains to mono behaviors, is that they kind of exist as these independent stacks where you can take a feature that's in your game right now that might be very expensive, where you really want to get those performance benefits, and rewrite that one first. Great, that one's rewritten, and everything else still works fine, everything's all good, and then maybe you're like, okay, well, we have a little bit more time before ship, let's optimize something else, right? One piece at a time. Could you restate what the other question was for me? Sorry, I forgot.
Basically, the improvements that are planned on the system, especially the burst compiler and so on, should I begin those efforts now, or should I wait till, let's say, some release 6 months down the road when the documentation is more refined, the tutorials are more refined, to begin that effort?
Right. Well, I mean, it's really very subjective, right? Depending on the kinds of games that you're making and kind of the scale and whether or not you're about to ship the game, right? I mean, ECS is certainly, you can use ECS in production, but it certainly isn't necessarily considered production ready at this point. So, I mean, really, at the end of the day, it's a risk versus reward type of way, right? If while we're developing the API, if you want to make sure that your game, as you plan to ship it, is going to be safe, and that the API is not going to change underneath you, which we generally try to avoid, just completely changing anything off the cuff. But yeah, if it makes sense for your project, if your project is coming out a little bit of ways away, then learning it sooner rather than later is probably better. And learning it sooner also helps us get the feedback, so that when you actually go to ship that game and you have those problems really laid out, you've already had a chance to use ECS, to try it out, to talk to us, give us feedback, to help you solve your problems.
Thank you. That's great work.
Yeah, thank you so much.
So I've been playing around with like the chunk iteration, especially on a component data, but I'm wondering if there's like an easier way to do like chunk iteration for shared components, because I do know like on the GitHub repo, there was a way to kind of like get the shared index and then remap it. Will that like be streamlined a bit, or would it be more of like avoided to avoid the abstraction?
So the nice thing, I'm not sure if you've seen this yet, because it was fairly recent, and if you have, sorry for going into it, but we just recently added a new API for chunk iteration, where you can actually get your archetype chunk arrays directly from a component group. And the nice thing about component groups is that they're filterable. So if you want to iterate via these shared component datas, and you want collections of chunks that match a certain component data query, then you can use the component group to actually filter out that data. And there's also a new job type that we introduced recently called iJobChunk, which is essentially just a job that you pass a component group to. And if that component group has a filter on it, then it's going to give you back an archetype chunk array that is correctly filtered.
Oh, okay, thanks.
Yeah.
Hi, thanks for the talk and the work on the API. I was just wondering, how would you recommend approaching the scaffolding? Like, would you like blocking things out? You might want to just use like Inject and things like that. But then, would you suggest like always drilling down and moving towards chunk iteration and things like that that are going to be more performant, or are there some things that you would just leave on the scaffolding?
I mean, generally, I recommend that use what you need, right? If the higher level scaffolds, if iJob process component data is all that you need for your particular system or for your particular case, go for it. But if you're interested in learning, if you want to learn the lower level APIs for the sake of learning them, so that you have the full understanding of them when you actually when you actually need that lower level functionality, then the sooner that you know that, probably the better for you, right? But I guess I would recommend, start on that kind of scaffolding chart, right? Start on the left side, start with the highest level scaffolds, and just dig your way down one by one as needed.
Okay, thank you.
So will there be, for say, iShared component data that are actually unmanaged or blittable with the new C# keywords for actually saying, hey, this is unmanaged, it's only primitives? Will there be a way to be able to either get the array, like an actual array or native list of those specifically shared types of indexes? Because sometimes I just have a shared index for a group and it's just a number, and I could pass it to a job, but the APIs for doing so per chunk are kind of awkward if you have that particular use case.
Right.
Because then you'd have to get a list and then put it into another native list or native array and then pass that to all your jobs and then look everything up. Will there be APIs that mitigate that problem, specifically in that case of unmanaged structs for iShared component data?
Right. So, I mean, for this specific problem, I'm not personally aware of a solution that we have in mind. But if this is a problem that you're having, I encourage you to go onto the forums and talk about this problem and say, hey, I just noticed, I've been doing this and going through all these hoops. Often those, we pay a lot of attention to the forums, and often when those forum posts actually result in an understanding that we find hey, there's something missing from our code base, then usually that actually winds up as, a Git issue that we eventually tackle. So I don't know of specific plans to solve that, but if it's a problem that you're having, and, we want to help you with that problem, so.
All right, I'll measure some use cases that I have since I've kind of stalled on that one area, but when I get back to it, I'll double check and let you guys know. Thank you.
Yeah, thank you so much.
Apologies if I misunderstood this, but if the chunks aren't contiguous in memory and you're iterating through them, aren't you still jumping around in memory locations?
You're still jumping around as far as like the cache is concerned, right? As far as the actual memory reads are concerned. So yeah, there's going to be a cache miss when you're going from one chunk to another. But the cost of component data array wasn't just the cost of a cache miss. It was also the cost of trying to reevaluate what index inside of that chunk array each chunk actually is. So if you read from index 100 and then 101, like it easily knows, okay, just go to the next piece of data. But if you try to go back to 50, then the component data array is like, okay, wait, I don't remember which chunk was at 50, so let me start at the beginning and just run all the way through it. But yeah, moving from chunk to chunk, there's still a cache miss that's associated with doing that operation. And we have some ideas on how we can improve that going forward, but as it stands now, there will still be a cache miss as you're jumping between chunks.
Great, thank you.
Yeah.
The discussion on the burst compiler appears to give us a new set of tools to further improve performance. However, if we use ECS at best practice, would you say that it's good enough for most coders that you don't really need to go down to the level of mastering the burst compiler?
Well, the nice thing about burst is that it directly takes advantage of a lot of the advantages that ECS gives you. Like one of the nicest things about ECS is that linear, within a chunk, that linear memory layout. And because of that, the burst compiler can easily take that code and vectorize it just automatically just for you, which is pretty awesome. And there's a nice burst inspector where you can see how that all works and how that vectorization is actually happening. So I would recommend, use the burst compiler. It's a tool that we're giving out. It's a pretty good one. And it doesn't, I haven't encountered an example where it added a significant amount of complexity to my code, but if that exists, if that's a problem that you've been having, then feel free to let us know and we can talk about how we can alleviate some of that complexity.
So in other words, most developers of Unity should use both tools hand in hand.
Yes, I think that both tools work best together. It's not just, okay, we take one tool which gives some benefit and another tool which gives some, like one actually makes the other more effective. So by using them both together, along with native lists and the job system and pretty much everything in the data-oriented tech stack, it's all being designed as an ecosystem that can kind of function kind of with itself in the best way possible.
Thank you.
When we were working with ECS, we were trying to compare the positions of like 5,000 entities to 5,000 other entities. Is there a good way to, or a preferable way to, in parallel, make comparisons between, n against n number of entities and do that as quickly as possible?
Mm-hmm. So there's no explicit API that is able to just do that problem generically in the best way possible. Really, at the end of the day, it's going to depend a lot on individual use cases, right? That n by n calculation, maybe you don't need to do n by n. Maybe you can kind of make that list smaller, or maybe you have some other optimization that you can do. So ECS doesn't currently provide an API that solves that exact problem, but hopefully using the tools that ECS has, you can solve that problem kind of externally from the system. But otherwise, really the best thing that you can do is just a big loop over all of those, all of that data, which can get pretty expensive, but
yeah. So that would imply that for those two groups of entities, when you're going to index something on the second one, that's doing all those lookups, right? Again, right? It's not prepared in any way.
If you're indexing with a component data array, totally. If you have taken that data and copied it to a native array, then you're not. Then you're using it as an array. You're still paying the cache miss issue, right? Where you have one when one job completes, it completes after reading all the way to the end of that array, and then it's going all the way back to the beginning. And if that data is sufficiently big enough to not fit in your L1 cache, then you're going to get L1 cache misses as you're kind of going through that data. Or if it's really, really big and doesn't fit in your L2 cache, then you have a pretty big problem. So,
Awesome. Thank you very much. Great work.
yeah, thank you.
Hi. So sorry to go back to the burst compiler, but is there a reason why you would ever not use the burst compiler? Like, is there a reason it's not? Why is it opt-in and not default?
The best answer I have for that is just that it's in development, and then we're still working on it. So it's not perfect, and it could have bugs, and it could, do something with your code or optimize out some instruction that's actually critical. But that's the only answer that I have. There's probably the burst team would probably have better answers to that question. But yeah,
Okay, thank you.
That's the best I got. Yeah. Cool. Thank you very much.